All right, let's talk about colligative properties. Now, this is a weird word, but don't be intimidated. It's just very easy. These are properties that depend on concentration. That's it. So it means that whenever you change the concentration of something in a solution, these are going to change. And it doesn't matter what it is, it just means that if you have more of the solute in the solution, these things are going to change, right? So we're going to look at four of these properties, right? So colligative properties are the solutions that depend on the concentration of the solute particles rather than their identity. So it doesn't matter what it is, it's just the concentration. And we have four colligative properties. So whenever you change the concentration, specifically whenever you increase the concentration in a solution, the vapor pressure is going to get lower. The boiling point will get higher and the freezing point will get lower, right? And then the osmotic pressure will also change and it will get higher. So whenever you increase the concentration, the osmotic pressure will increase. And we'll talk more about what all of these mean, but that's the main idea. Whenever you increase the concentration, these four things do change in the solution, and these are the properties we call colligative properties. Now, what we're going to do in this video is look at each one of them, know what they mean, and we're going to even look at how you can calculate the change in these properties. So we're going to look at a few formulas. So given the concentration, can we find out how much change we're talking about? All right, so let's start with vapor pressure. Now, vapor pressure, I talked about it in another video, but vapor pressure really is it's going to be, let me see if I can fit this in here. Vapor pressure is going to be to result in this escape of solvent molecules from liquid to the gas phase. All right. So if you look at this figure down here, I like it. The one with those pills right there, those represent water molecules. So if you have water molecules by themselves, and the vapor pressure comes from them escaping from liquid phase to gas phase, then if they are by themselves, it's going to be easier for them to just go from liquid to gas. But if you have, for example, salt molecules, those red molecules there, they're going to prevent the water molecules from escaping easily. So that's why we say that the vapor pressure gets lower. Now we're talking about there's this law called Raoult's law that governs that. We won't get too much into it. The main thing you need to know for now is that the molecules, the solute molecules, are going to prevent the water molecules or the solvent molecules to escape easily. And because of that, the vapor pressure will be lower. So that's vapor pressure lowering. That's the easy one. All right, let's go to the next one. Freezing point depression and boiling point elevation. So freezing point is going to get lower when you increase the temperature, the solute concentration, and the boiling point is going to get higher. And why do they do that? Well, if you're freezing water, for example, the solute molecules in water, if you increase the temperature, they're going to interfere. Because when water freezes, the molecules of water are just connecting together, they're getting together. Well, if you have something else in between, they won't get together as fast or as much. So because of that, these molecules are going to interfere. So that means that if you have water, usually water freezes at 0 degrees Celsius. I want us to establish that. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. So the freezing point of water is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. If you add salt or something else in water, the freezing point will get lower and the boiling point will get higher. Why will the boiling point get higher? Well, the same thing with the freezing point. The boiling point is, well, when you boil in water and it's, the molecules are going from liquid to gas. If you have a solute in there, it's going to interfere with the escape of those molecules, right? So those are two more colligative properties, but we're going to look at them in a little bit more detail. Let's start with freezing point depression. You can mathematically measure the amount of change on the freezing point. So this is the formula that we're going to use. Delta TF at the bottom there is how much our freezing point is going to change based on what we put into the water. So we're going to calculate it by using Kf. Kf is a constant, right? So it means that it's just a number that I give you. M is the concentration, because remember, the concentration is the one that affects this change. I is a little tricky, but think of it as the number of ions. That's it. But specifically, it's the number of particles, right? Because again, with these qualities, we're talking about particles that are in there. So let's say you have I can't write here, but let's say you have like NaCl. NaCl, right? How many particles is that going to be? Well, remember that NaCl or other ionic compounds dissociate in water. They're electrolytes. And that means that NaCl, when it gets into water, is going to divide into Na and Cl. Na plus and Cl minus. And these are what? These are ions, and there will be two of them. So NaCl, even though it's one compound, it's going to result into two particles. So I for NaCl is 2. So when we have ionic compounds, we're going to have a different number of particles. And look at this. If we have, for example, magnesium chloride, MgCl2, how many ions are these? How many particles? Well, look at it. It's an ionic compound, so it's going to dissociate. And when it dissociates, it's going to give us 1 magnesium atom and how many chlorine atoms? 2, right? So how many particles? 3. So MgCl3 will have an I number of 3, right? So that's how we're going to look at I. But this is only for ionic compounds, right? If you have covalent compounds, they won't dissociate in water, right? So I is very important to find when we're talking about these. Another one is boiling point elevation. So it's the same idea, but we're talking about boiling point at this point. So this one, delta TB, the change in boiling point, is going to be equal to KB, which is the molality. KB, which is the constant, M, which is the molarity, and I, which is the number of ions. That's the formula. So all you need to do is just see if I set it up. There you go. All right, all you need to do is just plug in the numbers, right? But also you might have to calculate the molality. By the way, the molality with a small m, I need to remind you that it's the moles of solute over the kilograms of solvent. That's the formula for molality, right? Not to be confused with molality with a big M, with a big M and small r, molarity. All right, let's look at an example. They're asking us first, what is the molarity? Let me move it down so that you can see it. What is the molarity of a solution that is made by dissolving those moles of ethylene glycol in kilograms of water? So this one is easy. They ask you the molarity, but we already know the formula for molarity. So they gave us, let's start by just, writing down what they gave us. They're asking the molarity with small m. They are giving us the moles, so the number of moles is equal to 1.25 moles. It's the moles of solute. And then the kilograms of water, which is water is a solvent in this case, is 0.45 kg. All right. So what do they want for A? They want the molality, which is the number of moles of solute over the kilograms of solvent. So all we need to do here is just substitute. We have the moles of solute, 1.25 moles over the kilograms of solvent, which is 0.45 kg. All right, what do we get? .25 over 0.45 is equal to 2.78. 2.78 m. That's the molality. All right, so we already know how to do that. But look at B. B is it's giving us the Kf for water, and it's asking us the freezing point of the solution. And we have to be very careful here. The usual freezing point of water is what? The freezing point, or TF, of water is 0 degrees Celsius, remember, right? Water freezes at 0 degrees Celsius. So the question is asking us, like, now that you've added the solute that we just figured out the concentration of above, what will be the new freezing point? In other words, we know that when you add something in the water, it lowers the freezing point. The question is, by how much? But we do have the formula for it, so there's no need to worry. But let's set it up correctly where we write down what we have. We have the freezing point, but we also have the molality that we just calculated above, so 2.78 molar. What else do we have? We have Kf, which is 1.86 degrees Celsius per mole. This is the constant, and then they're asking us the freezing point. So we gotta find the delta TF, which is the change in freezing point. So how do we find it? The change in freezing point is equal to, we just looked at it above here, right? Kf, which is the constant, times m, which is the molality, times I, which is the number of ions, right? Now, the number of ions, again, we looked at how whenever you have an ionic compound, you got to find the number of ions. But for this one, it's ethylene glycol. Ethylene glycol is a covalent compound. It's not an ionic compound. So I is equal to 1. So for a covalent compound, I is going to be equal to 1. For an ionic compound, I is going to be the number of ions, right? So here, I is equal to 1. So we really have everything we need here. So delta TF is going to be equal to Kf, which is 1.86 degrees Celsius per m, times the molality, which is 2.78 m, times I, which is 1. And this is 1 mole electron. So this is going to be equal to 1.86 times 2.78. .17. So is equal to 5.17 degrees Celsius. This is 5. All right, wait a minute. We're not done. We just found the change in freezing point. So what this number is telling you is that the freezing point has changed by this much when we added the chemical above. But here's the thing. This is just a change in freezing point. We have to find the actual freezing point, the new freezing point when there's this change. So think of it this way. Let me just write it up here. So the change in freezing point is going to be equal to the new freezing point minus the original freezing point, right? So let's just call it old, right? So this is the change. So what does that tell us? It tells us that if the original freezing point is 0 degrees Celsius and the change is 5.17 degrees Celsius, right? To find the new temperature, we're going to take the 0 degrees Celsius, because remember, they told us that the temperature lowers, the temperature gets lower, the freezing temperature gets lower. So we're going to take the 0 degrees Celsius minus 5.17 degrees Celsius. So the new freezing temperature is going to be equal to the negative 5.17 degrees Celsius, right? That's the answer, because the freezing point lowers, and this freezing point lowered by this much. If we're working on boiling point and we calculated it for boiling point, guess what? Instead of adding here, instead of subtracting here, we will add, because the boiling point goes up, right? So we'll take 100, which is the original boiling point, and then add the delta TB that we've calculated. That's how you calculate the boiling point elevation and then the freezing point depression, right? All right, I think that's enough for that. Let's look at one last colligative property. So we've already looked at pressure, right? Vapor pressure, we looked at boiling point, we looked at freezing point. Now let's look at one last thing that changes when we change the concentration. We call it osmosis. You probably have heard osmosis before, but if you haven't heard of it, it's very cool. It doesn't just happen in a chemistry lab. It happens in our cells, in our body. It's happening to you right now. It's the movement of a solvent, right? I've highlighted these because these are the three things that are really important in an osmosis. It's a movement of solvent, and the solvent is moving from a dilute side to a more concentrated side, and it's going through a semi-permeable membrane. What's a semi-permeable membrane? It's exactly what it sounds like. It's a membrane that's permeable, but it only lets the solvent through. Lets the solvent through and not the solute. So if you can pay attention to this figure at the bottom right here, so we start here, right? On side A, you have a high concentration of your solute. On side B, you don't have anything, right? You don't have much of a concentration here. So what will happen is, if you have a semi-permeable membrane, the solvent is going to move from a lower concentration to a high concentration. And this just doesn't just happen again in a tube like this. It happens in your cells as well, because your cell membranes are semi-permeable membranes. So osmosis has three things. Why are we talking about this? We're talking about this because this requires pressure. And this pressure, we call it osmotic pressure. And guess what? This pressure depends on the concentration, or otherwise the amount of solute that we have. Right? So it's the amount of pressure required to stop that flow. What's the formula for it? It's M, which is molarity, R, which is a constant, T, which is a temperature in Kelvin, and I, which is the number of ions. That will be the pressure, the osmotic pressure for that solution. Let me give you an example. Calculate the osmotic pressure of a 5 times 10 to the negative 2 molar solution of NaCl at 25 degrees Celsius. And 25 degrees Celsius is 298 Kelvin. We need to use Kelvin. So the osmotic pressure that we designate as pi is equal to mRTI. And remember that I is what? It's the number of ions. So for NaCl, I is 2. So for this, we have everything, right? M here is 5 times 10 to the negative 2m. R is 0.082 L atm over mole Kelvin. T is temperature. We have it is 298 Kelvin. I is what? Is 2 because you have NaCl. All right, so 0.05 times 0.082 times 298 times 2. So 2.44. That's what I get. 2.44 ATM, by the way. You write it in ATM because it's pressure. It's in the atmosphere. That's how you calculate the osmotic pressure. All right, so this osmotic pressure is actually applied in the cell, right? So if you have a cell, for example, that has a certain solvent, so just a circle represents a cell here. If the solvent outside is lower than the solvent inside, we call this a hypotonic solution. And what happens is the solvent will go inside the cell and the cell is going to swell and eventually burst. If the concentration outside is higher than the concentration into the cell, the solvent gets out. This is the osmosis and osmotic pressure, and you have a hypertonic solution. Hyper meaning we have high tonic solution, right? Isotonic solution is when you have the same concentration in and out. And how does it apply to cells? It looks like this. This is an example of a blood cell. Whenever you have a hypertonic solution, your cells start to shrink, right? And you have blood conditions that happen. Whenever it's an isotonic solution, it's nice and great because we have, a balance and everything is good. When you have a hypotonic solution, this is the one where the solvent goes in and then your cells start to burst. So you have blood conditions that people are dealing with right now because of this. By the way, another example of this is when you are making a pickle or a cucumber or something like that, right? You put your cucumber in a concentrated solution, and guess what happens? The solvent, which is water in this case, is going to move from the cucumber to the outside, and that's why it becomes smaller. So it is a hypertonic solution that you just made. All right, but that's enough for osmosis, and that should be enough for colligative properties. Remember, so as a quick reminder, you have 4 of them: lowering vapor pressure, increasing boiling point, lowering freezing point, and then increasing osmotic pressure. And now you not only know the effect, but you can actually you can calculate how much this has changed by the formulas that I gave you. And I think that's enough. That's enough for today. I'll see you next time.